Boom. All right, Julien, welcome. We are in chapter 4 right now. Yeah, chapter 4 is colligative property. In the last chapter, we're discussing stoichiometry. And stoichiometry is one of the topics that actually is the heartbeat of Chem 1 to 2. The two major topics in Chem 1 to 2, that involve calculation that can take 50% of questions in exam is stoichiometry and AB reactions, right? Acid-base reactions. So let's quickly look at colligative property, although it happens to be the shortest topic in the whole Chem 1 to 2. But be that as it may, let's see what this chapter holds for us. So first, colligative property. Now, when a solid actually is added to a pure solvent, a solid, maybe salt, maybe anything that can dissolve in water, is added to a pure solvent, usually changes are noticeable, right? Changes like change in color, change in concentration, change in temperature, stuff like that takes place. But the properties that are solely related to the quantity of solute added to a particular solvent is referred to as colligative properties. Those properties that you see as a result of the amount of solute, the amount of sugar you added in water, is referred to as colligative properties, right? So colligative properties are solely dependent on quantity of solute present in a solution. Common colligative properties include number 1, lowering of vapor pressure of the solvent. Number 2, molar elevation of boiling point of the solvent. Number 3, molar depression of the freezing point of the solvent, aka cryoscopy. As for molar elevation of boiling point is also called a boileoscopy. Then number 4, exhibition of osmotic pressure. Let me put it in a language that you are likely going to understand better. These properties I have just mentioned are called colligative property. Why? Simply because these properties of a pure, simply because these properties affects the properties of a pure solvent when a calculated amount of solute is introduced into them. Let's take, for example, I take sugar, and pour into a container containing pure water that is free of impurities. You will discover that the sugar solution that will dissolve in this water will make the water to become less volatile, or let me say it will decrease the vapor pressure of the water. Now, when we talk about vapor pressure simply implies the ability of a substance, usually liquid or gas, to change its state easily. That's vapor pressure. The vapor pressure of a liquid is simply the tendency of that liquid to easily change its state from liquid to gas. And usually this is achieved by increase in surface area, increase in temperature, increase in pressure, blah, 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 blah. So when you add solute into water, like sugar solution into water, if that water could vaporize at 100 degrees Celsius, you will discover that because of the presence of the solute, it will vaporize at a lower temperature. So it will lower the vapor pressure of the solvent, right? Next, assuming the vapor pressure of the solvent is 100 atm. By the time you add sugar solution to it, the vapor pressure will drop down to about 90 atm. That's what we mean. As for molar increase in boiling point, if you add a sugar solution to a pure solvent, e.g. water boils at 100 degrees, everybody knows. But because you have added sugar solution to it, it will demand a higher boiling point for that water to boil. That water can no longer boil at 100 degrees Celsius because of the introduction of more solute, and that solute increases the boiling point. And that process is called a boileoscopy. Now, the reverse of it is the molar depression of freezing point. Molar depression of freezing point is key. How does it bring about decrease? Anything that brings about increase in boiling point automatically brings about a decrease in freezing point. You don't need to be told. Automatically brings a decrease. So if I add sugar solute to a pure solvent, if that solution is supposed to freeze, or the solvent itself without the sugar is supposed to freeze at 0 degrees Celsius, the presence of that of that solute in that solvent will make that solvent, which is called a new solution now, to freeze at what temperature? To freeze at a temperature lower than 0 degrees Celsius, which is -2 or -3. That is what a solid will do to the freezing point of a solution or of a solvent, as the case may be. Then the last part of it is the exhibition of osmotic pressure. You know, all substances in total, when they are pure, they have no osmotic property. There is no movement of water molecules from one region to another because the solvent is absolutely pure. Concentration is equal in all dimension. But as soon as I introduce sugar solution and the sugar sinks to the bottom, there becomes a high level of concentration at the bottom of the water. And so you discover the sugar solution will start either diffusing or moving from a concentrated area to a less concentrated area, or from a lesser concentrated area being the solvent into the sugar. That is osmosis or diffusion. So there's going to be movement. There's going to be osmotic properties exhibited by the pure solvent. That is what we mean. And that is what this chapter is all about. So we are going to take them one after the other. We start with the very first one there, which is lowering of vapor pressure. In calculating problems in here, we make use of what we call Rao's law. Yes, Rao's law is key. But before I talk about Rao's law, it is important for you to know that the number of ions in a compound is inversely proportional to the vapor pressure of that compound. I take it again. The number of ions present in a compound is inversely proportional to the vapor pressure of that compound. And that simply means that if I have how do I put it this way? If I have a compound made up of two ions, for example, sodium chloride, the vapor pressure of sodium chloride is far higher than aluminium oxide. How do I mean? Sodium chloride has two ions. Therefore, it has a very high vapor pressure because it has a low number of ions. But look at aluminium oxide. Aluminium oxide has 5 ions. 2 aluminium ions and 3 oxygen atoms. So that's 5 ions in total. And the number of ions is higher. So the higher the number of ions, the lower the vapor pressure. That's one thing you must take note of. Then number 2, calculating questions or calculating stuffs related to this chapter will draw your attention to Rao's law and Henry's law as well. Although Henry's law is not very much applicable in this your course area, and more emphasis is placed on Rao's law, which states that the vapor pressure of a solvent is the product of the vapor pressure of a solution is the product of the vapor pressure of the solvent and its mole fraction. The vapor pressure of a solution is simply the product of the vapor pressure of the solvent and the mole fraction of that solvent. And what does that mean? This takes place at constant temperature and as constant volume. Very, very important. That is Rao's law. Vapor pressure of the solution being directly proportional to the product of what? Of the mole fraction of the solvent and the vapor pressure of the solvent. Now, this can also be expressed in the form of solute, that the vapor pressure of the solution can be the mole fraction of the solute and that of the solvent. That's a shorter cut anyway. Then, it is important for you to know that change in vapor pressure is the vapor pressure of the solvent minus the vapor pressure of the solution, and not the other way around. You can't say vapor pressure of the solution minus that of the solvent. It wouldn't work. The reason is because the vapor pressure of the solvent is always greater than the vapor pressure of the solution. Now the big question is, why and how can the vapor pressure of a solvent be bigger than that of a solution? Every solvent that is pure automatically has a higher vapor pressure than a solvent that has been adulterated. And that is why one of the colligative properties will tell you that introducing a solute in a solvent will lower the vapor pressure of the solution. So the pure solvent has a higher vapor pressure than that of the solution. So you say vapor pressure of the solution of the solvent minus that of the solution. Now that takes us into the details of Rao's law. Sorry, I want to say Henry. Now, according to Sir Henry, but before I talk about Henry's law, it's important for you to know that Rao's law is applicable to real gases, like oxygen, nitrogen, carbon 4 oxide, sulfur 4 oxide, sulfur 6 oxide, just name them. But as for Henry's law is applicable to ideal gases. When we mean ideal gases, we mean perfect gases, gases that do not have intermolecular force of attraction existing between them. gases that behave in a perfect manner, gases that lose no energy on collision with each other. These are hypothetical gases, and that is where Henry's law comes into play. And according to Sir Henry, as for him, his law states that the mass of a dissolved gas in a solvent is directly proportional to the partial pressure of that gas. That simply means that as the mass of the gas dissolves in a solvent, so does the partial pressure of that gas increases. So it's a direct proportionality. So as much mass dissolves into a solvent of a gas, so does the vapor pressure of that gas increases. So it's a direct proportionality, mass and vapor pressure, or partial pressure as the case may be. Let me use the word partial pressure because that's the actual word used here. Mass of a gas dissolved in a solvent is directly proportional to the partial pressure of that gas. That's Henry's law, applicable to ideal gases and not real. As for routes, it's solely applicable to real gases. So that takes us to some work example on Raoult's law. You may just be asked, 18 grams of glucose is dissolved in 5.4 grams of water to give a solution of X vapor pressure at 45 degrees Celsius. Given that the vapor pressure of pure water is 100 atm at the same 45 degrees Celsius, find the value of X and the change in the pressure. In other words, find the value of the vapor pressure of the solution. Well, that is simple. If you remember, vapor pressure of the solution is the mole fraction of the solvent times the partial pressure of the pure solvent. The partial pressure of the pure solvent is given to us as 100. You have to calculate the mole fraction of the solvent. And the solvent we are talking about here is water. So you are given the given mass of the water, calculate it, divided by its molar mass to get the number of moles. You are given the mass of the solute, divided by the number of moles to get what? To get the number of moles, divided by the molar mass to get the number of moles of the solute. And by the time you do that, you discover that you will have the number of moles as 0.1 and 0.3 respectively. 0.3 to water, 0.1 to glucose. So for me to calculate the mole fraction of the solvent, it will be water all over the solution. So I'm going to have 0.3 divided by 0.1 plus 0.3. So times the vapor pressure of the solvent, which is 100, and that will give me 75, right? So by the time I get this, for me to calculate the change in pressure, I have to find the difference between the pressure of the solvent and that of the solution. Pressure of the solvent is 100, that of the solution is 75, and that gives me 25 at the end of the day. If, however, you want to follow a shortcut and you want to just look for the vapor pressure, the change in the vapor pressure directly, then you can just use change in vapor pressure, which is the pressure of the solvent times the mole fraction of the solute. That means I'm now using 0.1 divided by 0.1 plus 0.3 times 100, and that will give me 25 on a platter of gold. You get it? If you don't get it, forget about it. So that takes us to the next one there, which is ebullioscopy and cryoscopy. Now, ebullioscopy simply means molar elevation of boiling point, while cryoscopy simply means molar depression of freezing point. When a non-volatile solid is introduced into a pure solvent, it increases the boiling point of that solvent, but decreases the freezing point of that solvent. Now the big question is, by what quantity does the boiling point increase, and by what quantity does the freezing point decreases? That is calculated from this relationship. As for the boiling point increase, the formula is change in temperature, that is change in TB, being equals to KB times M. KB is the ebullioscopic constant, which is always measured in degrees Celsius, Kelvin, in degrees Celsius per kilogram per mole, or simply put, degrees Celsius kilogram per mole. So it is always rated in 1 kilogram. Now, also take note, at times they can give you this KB to be in hundreds of grams instead of thousands of grams. If it is in thousands of grams, that's the standard kg. But when it is given to you in hundreds of grams, you have to be careful, because the formula for molality that uses 1000 will now use the 100, which is given to you. If it was 10, you use the 10. Right? So molality, if you remember vividly, it is the amount of solute present in 1000 grams of a solvent. right? So the amount of solute in moles present in 1 kilogram of a solvent is what you refer to as molality. And the formula for molality is simply mass all over the mass of the solvent times the molar mass of the solid. So mass of the solid times 1,000 divided by the mass of the solvent times the molar mass of the solid, right? Very important. So that is that. And the new boiling point will be the old boiling point plus the change in boiling point. Yeah, it's going to be plus because there's increase. Now, as for cryoscopy, the formula you will use in calculating here is change in TF, which is change in the temperature of freezing point. It's going to be TF times M. M is molality, not molarity. Molality. TF simply represents the cryoscopic constant. Of course, it is also measured in degrees Celsius, kilogram per mole. Right? Take note, the cryoscopic constant here is also referred to as the depression constant, okay? Or molar depression constant, as the case may be. And the formula for the cryoscopic constant, or the formula for change in freezing point, is simply 1,000 times Kf times the mass of the solid divided by the mass of the solvent times the mass of the molar mass. Sorry, times the molar mass of the solid. Good. So you have to remember that vividly. And in some cases where density is given to you in the place of the mass of the solvent, you can always multiply the density by the volume of that solvent. You get it? And then also in some key places where you are given volume of water instead of the mass of the water as the solvent in centimeter cube, remember that 1 gram is equivalent to 1 centimeter cube. So no matter the grams, no matter the cm cube they give you, just convert it to gram. If 1 gram is equivalent to 1 centimeter cube, then if they're giving you 500 centimeter cube, it's equivalent to 500 grams of water. You get it? So you can always medal that in your formulas and get the job done. So the new freezing point becomes the old freezing point minus the change in freezing point. Yes, minus, because there is decrease in the freezing point. All right, so the next thing there is taking us to the last part of this chapter, which is called exhibition of osmotic pressure. And then, of course, the formula that champions exhibition of osmotic pressure is the ideal gas equation, PV equals nRT. And there are basically 4 formulas that you must put at the back of your coconut. Number 1, PV equals to nRT. Number 2, change the number of moles to mass over molar mass. Insert in that formula. That gives you the second formula, which is mRT divided by molar mass. Then number 2, in case you are given constant, just make number of moles over volume the value of C, and you come up with pressure to be equals to CRT. So that gives you the third formula. Then the fifth formula will be in a case where you are given density. And you know density is what? Mass over volume. So just change the number of moles to mass over molar mass, and then make mass over volume the value of D, and you will come up with this formula that says that pressure equals dRT all over the molar mass. Boom, that's the end of this chapter. And we have done justice to this chapter. So in the next class, we are going to be looking at, I think this is chapter 4, right? Yes, the next class, we are going to be entering ABS. As soon as we finish ABS, we take AB reactions, and that is the end. Thanks for listening. Boom.